Uh, let's get started. So this is the third week, second class, and today I hope I will complete the simplex method. So, so we discussed on Wednesday all the ingredients we need for developing the simplex method. So we will try to go through the full method today and also discuss some of the related issues that you have to think about in implementation of the method. Okay. And heading up, we will that will move us next week. We will discuss duality theory. And just as a reminder, for next week, the class will not be on the Wednesday. I'm out of town next Wednesday, so we will do the class on Thursday at 2 p.m. It will be either in this room or the next room, one of these two rooms. Okay. So next week the class will be on a Thursday. Okay. 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 So let's start with the simplex. So I think so just a quick recap of some concepts, okay, which we will use today. And in fact, I will start with maybe actually I'll start with the algorithm itself. So I'm going to now first describe the simplex method, okay, using a tableau. So as I do this, I will also revise some of the concepts that we require uh, um from last class. So you'll remember basically. So simplex method using something called a tableau. Okay. So we are going to discuss this method. Okay. So the way we are going to implement the simplex method, remember, is we have a basic feasible solution, which we know is optimal. Okay. So we are going to start at some basic feasible solution and try to move towards better basic feasible solutions. And the key thing we need is we need a direction in which to move. And so an appropriate direction, which in the simplex method we identify by figuring out which non-basic variable to increase and other ones set at zero, the other non-basic variables. And then we are going to look at reduce costs, which tells me how much the objective changes. Okay. So the way the method can be implemented using the Tableau method is the following. So at every step, so at any iteration or any step, the Tableau will look like this. You will have four components to this, which are going to be kept track of. Okay. First is the value of the basic variables. Okay. So remember, my basic variables have this formula B inverse B, which is the non-basic variables of zero. And remember, throughout our simplex tableau is our simplex is in standard form, ILP is in standard form, AX equal to BX non-negative. So my non-basic variables are zero, and my basic variables have this form, B inverse B. The second part of this is we're going to keep track of this matrix B inverse A. On the top row, we are going to keep track of the reduced cost vector, which is C bar transpose in a row vector form. And the definition of this was C transpose minus CB transpose B inverse A. And in the top left column, top left entry, we're going to keep track of the objective function at this basic feasible solution, except we're going to keep track of the negative of this. This is required for the bookkeeping, okay, for the algebra to work out correctly. Okay. Okay. So what is this capturing? This is capturing information on the current basic feasible solution. Okay. So at every iteration, we are going to, so remember, an iteration means a basic feasible solution corresponding to a basis matrix B. All the information I require at this point in terms of the basic values, the basic variable values, this B inverse A matrix, the reduced cost, and the negative objective function is stored in this tableau. So what the simplex method is going to do is as follows. So step one, we start with a basic feasible solution. Okay. And we will discuss later on in the second half of this class how might we identify a basic feasible solution. Sometimes it's easy to find basic feasible solutions to start off the problem. Sometimes it's not as easy. Okay, so we'll come back to this. But suppose I have a basic feasible solution. I can create a matrix. I can create a table or a tableau of this form. The second step will be I need to figure out which variable should so the simplex direction is what? Try to find a non-basic variable to increase. And how do I do that? By looking at the reduced cost vector. Okay. So identify, so choose a variable to enter the basis where the variable has a negative reduced cost. Okay. So why is this? Because we saw last class that um, so remember, I'm trying to minimize the problem. Okay. So my goal is to identify basically, so if all my reduced costs are non-negative, I'm optimal basically. Okay. So what I want to do is I want to work towards that. So if I find a variable with a negative reduced cost, okay, it's something I want to get into my basis basically. Okay. And I want to move something out of my basis. Okay. So next, what we are going to do is we're going to identify. Okay, so this is a direction in. So I would like to increase. So I would like to increase this xj variable, and thereby decrease my objective function. Okay, okay. Then I will identify the variable to leave the basis, and I will do all these steps. Okay, we'll do an example. Identify variable to leave basis using the minimum ratio test. So what is this test doing? So once you decide you want to bring a non-basic variable into the basis, it forces the basic variables to have this. There's a formula for the basic variable direction, b inverse a, minus b inverse aj, and we saw last time that depending on what the signs of those the direction vector is, when you move to a new basic feasible solution, it might be the x plus theta d might become negative. So you can't choose theta arbitrarily. So you have to choose some theta which you find by this minimum ratio test, and that will basically force one of the variables to go to zero. So the basic variable is going to become non-basic. So this variable is going to leave the basis. A variable is going to enter the basis, and then what we are going to do is once we identify the leaving and the entering and the leaving variable in this order, okay, we're going to do row operations. Do row operations, okay, using the so this the variable that leaves forms what's called the pivot row. Okay, so do row operations using the pivot row. Okay, to um, to make uh, the column vector in the matrix. So column vector in the tableau for the entering variable and unit vector. So we're going to do a transformation, and the reduced cost make it equal to zero. Okay, so the idea is that we are going to use this variable to enter the basis. It's a non-basic variable. So once it enters the basis, basic variables will always have zero reduced cost. So I have to do row operations to make the basic variables have a zero reduced cost. And I'm going to make that column corresponding to the entering variable a unit vector. So there's going to be a one where the pivot row is zero everywhere else. Okay, and we'll see why this row operations make sense. And we're going to continue doing this. So continue or repeat till all reduced costs are greater than equal to zero, which is an optimality condition, or we will identify the LP as an unbounded optimal value. I will tell you how you can identify this. Okay, so that's the algorithm. Okay, at the highest level. Okay, at every step we're going to identify a variable to enter the basis, a variable to leave the basis, do row operations, move to a new basic feasible solution, repeat this till we have an optimality certificate. Okay. Okay. And just as a broader point here, if you look at what these rows capture is, if you think about my simplex, I've got these equality conditions AX equal to B. So in this part, essentially what we are doing is what we are storing in this part of the table is just you're pre-multiplying both sides by B. Okay. So at every iteration, actually what we are doing is we are doing a pre-multiplication by a B inverse matrix. Okay. So this is what is being stored here, essentially. Okay. 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 Any questions with the broad algorithm? We'll do an example, it'll get concrete then. Okay. Any questions with the algorithm broadly? So what you have to remember is reduced cost vectors have to be non-negative for optimality. This is an important, we saw this last class. How do you identify optimality? And that will depend on So you want to make this vector non-negative. It's a minimization problem. Okay, everything is a minimization problem. Remember, we are solving here. Again, I mean, it should have been clear, but we are always solving a standard form LP, okay? The entire simplex method is developed for this problem. Okay. Okay. So we'll do an example. Okay. So I will take the example from last class. Okay, and we will just continue with that. So this was the example that we looked at. So I started with this, but now we will implement it and we will solve it to optimality. Okay. So this was a standard form LP. I'm just taking this from last class. I'll just remind you what the LP is. Okay. But we did this. We just started on this LP last class. Okay. 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 So this is an LP in standard form. Okay. I'm doing a simple example just to illustrate all the steps. Okay. So in this LP, we have x1 and x2 variables, and we have a set of, originally we had a set of 3 less than equal to constraints. I added in some slack variables and I made it equality. So this is a standard form LP where we have 3 equality constraints and 5 variables. Okay. And I think I plotted this last time. The feasible region, it looks like this. Okay. Okay. So we're going to first start at a basic feasible solution. So we're going to start at O. Okay. And I think we did this last time. So at this point O, so this is my starting BFS. Okay. And in this example, it's very easy to identify a starting BFS. Okay. How do you identify a starting BFS? It's actually very simple. This problem is these are LPs where the BFS is easy to find. How? Make x1 and x2 go to 0. S1 is 1, S2 is 4, S3 is 2. All of them are non-negative. That's a BFS. 3 equality conditions which are satisfied uniquely once I make x1 and x2 go to 0. And they are non-negative. Okay. So BFS here is easy to find. It is simply my basic variables here will be S1, S2, and S3. So in my tableau, so I write down my 5 variables, x1, x2, S1, S2, and S3. I've got 3 basic variables, S1, F2, and S3. Okay. What are my basic variable values? 1, 4, and 2. So this is B inverse B. Okay. So in this, at this point, just to remind you, what is B? My B is the columns corresponding to my basic variables, S1, S2, and S3. That's simply the identity matrix 1, 0, 0, 0, 1, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay. The columns corresponding to S1, S2, and S3, my basic variables. Okay. So clearly B is identity, B inverse is also identity. So if I do B inverse A, it has to be just A, which means that in this part of my tableau where I have to put B inverse A, I will just write down the A matrix. What is the A matrix? It's 1, minus 1, 1, 0, 0. So I'm just reading the entries here 2, 1, 0, 1, 0, 0, 1, 0, 0, 1. Okay. And the last thing I need to put in here is the reduced costs. Okay. So what are my reduced costs? So my reduced costs, so C bar is what? C transpose minus CB transpose B inverse A. This is the formula. All my basic variables are my slack variables, S1, S2, S3. They have no contribution to my objective, which means that the CB is simply 0. Basic variables have 0 cost. So I have to just write down the costs corresponding to my original problem. So the reduced cost for the starting basic feasible solution is just the original cost vector, which is what? Minus 3, minus 2, 0, 0, 0. And what is my objective function? My objective function here is x1 and x2 are 0. So my objective is 0. So here my objective is just negative of 0, which is 0. Okay. So that's my starting basic feasible solution. Okay. Any question with this, with all the different parts of this? matrix of this table. Okay. So now what do? We look at, so last time I moved in some direction towards E. Okay. How do I do that? Basically, we want to solve this LP. So we want to move in, we want to identify variables which have a negative reduced cost. Okay. Which means that in that direction, if I was to increase that variable, it's going to decrease my objective function. Okay. So I could have chosen X1. So both X1 and X3 have a negative reduced cost. So I could choose either one to decrease, to enter my basis. Okay. So here you can see there are some algorithmic uh, flexibility available. I've got two possibilities, X1 and X2. One is -3, one is -2. How do I interpret -3? For unit change in X1, I expect my cost to decrease by 3 units. For unit change in X2, I expect my cost to decrease by 2 units. Of course, I may not be able to make a unit change because the theta might restrict me in some way. Okay. But you could have chosen either one. Okay. So let's choose X1 for now. That's a choice. Okay. So remember, there's a choice, and that's where simplex method requires some refinements. You have to have some rules for choosing the entering and exiting variables. But among negative reduced cost, I can choose any one. So let me choose for now X1. So I choose X1 because X1 has a negative reduced cost. Okay. So let's say, so suppose entering variable is X1. It's not the only choice. You could have chosen X2 too. Okay. Okay. Because C1 bar is negative. Okay. So now I have to do my minimum ratio test. Okay, so what is my minimum ratio test doing? X plus theta d has to be non-negative. Now remember, my matrix, my tableau keeps track of B inverse A. Okay, the direction actually is minus B inverse A, the DB basic direction. So the way you're going to implement the minimum ratio test is because of that, the fact that we are keeping track of B inverse A, you will look at the ratios between the basic variables and this corresponding B inverse AJ column and do this for all the positive coefficients. Okay. So we're going to find theta star, the ratio test, by doing the minimum of 1 by 1, all positive. You have to look at all positive coefficients here. 4 by 2. Okay. 2 by 0 is basically infinity. So it's not going to restrict me in any way. Okay. So if I do 2 by 0, I'm going to get an infinity value there. Okay. So if you take the minimum of these two, it's going to be 1. Which means that the minimum is attained by the first, this row. So my exiting variable will be S1. So exiting or leaving variable will be S1. Okay. Which means I'm going to use this row. So that's my pivot row. And that's my pivot column. Okay. So all my row operations have to be done now using this pivot row. Okay. And what are my row operations? My row operations are, I want to make this a unit vector and make this reduce cost 0. Okay. And I have to do this using only the pivot row. So let me just number these rows. Let's say this is row 0, row 1, row 2, and row 3. I need to do all my row operations using row 1. Okay. Okay. So how do I do this? So clearly my row operations are to do row 0. So what are my row operations? So I will take row 0 and I will transform this by doing row 0 plus 3 times row 1. Okay. That will make this minus 3 plus 3 times 1, which is 0. This is a 1. I don't have to change anything. This is a 2. So I need to make this a 0. So I'll do row 2 minus 2, row 1. And this is a 0. I don't have to do anything. So I want to make this a 0, 1, 0, 0 vector. Okay. Is that clear? So now you do this and write down what the new table is. Okay, just do this. Of course, when you do this row operation, you have to do it throughout the table. Okay. So if you were to do this, any questions here with this step? Is it clear, all the steps here? Okay, fine. So what will we do? So we will have x1, x2, S1, S2, and S3. And if you do those row operations, and you can check this on your own, you will get values which look like this: 3, 0, minus 5, 3, 0, 0. Okay. And remember, I brought, so my S1 has now come out of my basis and X1 has come in. So S1 and X1 S1 will become X1. Okay. And then I'll have S2 and S3. And if you write down the values after doing that row operation I just told you, you will get 1, 0, 0, minus 1, 3, 1, 1, 0, 0, minus 2, 1, 0, 0, 0, 1. Okay. And you can check this. Just do those two row operations. Do it throughout. So for example, this will become what? Let's just take the top row, row 0 plus 3, row 1. So this will become 0 plus 3. That will become a 3. This will become 0, minus 2, plus 3. So minus 5 and so on. Okay. Okay. What is this point? This point is x1 is equal to 1, x2 is equal to 0. That's a non-basic variable. Of course, S2 is 2 and S3 is 2. Okay. And you can calculate S1. Okay. S1 is also 0 because it's a non-basic variable. Okay. So what is this point? So initially my point was O. This is the point E. So we have now moved to point E. And have we done a better job in our objective? Yes, because originally my objective was 0. Now I chose to move in a direction where the reduced cost was negative. So my objective has now actually gone down to minus 3. So this is always the negative of the objective actual cost. So my true objective is minus 3. So I've gone from 0 down to minus 3. I have improved my objective function value. Now we need to repeat. Okay. So what should be my next entering variable? X2. Why? Because X2 has a negative reduced cost. Okay. So if X2 enters my basis, my leading variable, so to find I have to do my ratio test. What's my ratio test? I do theta star minimum of, now that is a -1 here. Okay, so -1 will not, so I have to do the ratio test only with the positive entries. Okay, because essentially when it's a negative entry, it doesn't, uh, you remember when we did x plus theta d, that test, only some signs, when it's a negative sign, basically it will not constrain me to go in any direction. My constraints on my non-negativity of my basic variables of my variables will only show up for the positive coefficients. So I have to do the ratio test for 2 by 3 and 2 by 1. Okay. Which will give me a value of 2 by 3, which means that my leaving variable should be S2. Okay. So that's my pivot row. Okay. Again, you can see that we could have sometimes have had a tie here. Okay. Then again, if you have a tie, there are some algorithmic choices you have to make. Suppose both of them gave me a value of 2 by 3. Which one do you choose? You could have chosen any one, that's fine. It does have some effect on the convergence of these algorithms. Okay. We'll come back to that later. But as long as you have whichever one attains the minimum, you take that for now. Okay. There's a unique minimum here. We pick that. Okay. Okay. Now we do row operations. Again, there is row 0, row 1, row 2, row 3. You repeat. Okay. So for example, let's first just transform row 2. So row 2, you make it a 1 here. So you divide by 3. Okay. Next. So once I make this a 1, now row 0 will be row 0 plus 5 times row 1 because it's now become a 1. So I'm thinking of first doing this step. Okay. So now in my mind, this has become a 1. So now minus 5 plus 1, 5 times 1 will make it a 0. Then I do row 1 plus row 2. Row 1 will be transformed to row 1 plus row 2. And last one I will do is row 3 will be row 3 minus row 2. Yeah. Sorry, it should be row 2. Yeah, you're right. It should be row 2. You're right. Thank you. Yeah. Everything has to be with respect to row 2. Okay. all your row operations have to be with respect to the pivot row. Okay. Okay. So if you do that, and if you write down you write down the values, I'll just give you the values here. It's 19 by 3. I will explain why the row operations make sense in a bit. Okay. Right now, I'm just giving you the algebraic. No, this is the implementation. Why is this the right way to do it? And why does this work? I will explain that to you after this. Okay. But let's go through one round of this. So this now what I'm writing down here is just by doing these row operations. Okay. And I'm sure you can do this on your own. Just check out that these values, I should not have made any mistakes, but you can check it on your own. Okay, but let's look at what this point is. Okay. So what is this point? Now x1 is 5 by 3 at this point, and x2 is 2 by 3. Okay. 5 by 3 and 2 by 3. Where is this point? Okay. So, and what are 0? Essentially, S1 and S2 are 0. Where are S1 and S2 0? S1 is 0 on this line, S2 is 0 on this line. So we've actually moved to the point D. So we went from O to E. Now we have gone from E to D. Okay. So we are now moved to point D. And this was a good move because my objective was initially 0. It went down to minus 3. It's gone down to minus 19 by 3. So that's minus 6 point something. Okay. So we are decreasing our objective every round of the simplex method. Okay. The problem, of course, is I can't quickly go from here. I don't know why the optimal BFS is. So I'm going along the corners till I converge. Okay. Okay. So we are still not done because we still have a negative reduced cost. Okay. So we'll have to continue. Okay. So we continue. So the entering variable is S1. So entering S1. Yes. What is the leaving variable? 5 by 3. So theta star is the minimum. So let me write this here. Any questions? Am I going too far? It's okay, right? This is largely algebraic and it's not particularly hard to do once you understand the steps. So what is theta star? Is the minimum of 5 by 3 and 1 by 3. If you take the ratio, that's 5. You don't have to do it for negative value. 4 by 3 and 2 by 3, that's a 2. So my exiting variable has to be, so this is 2. So my leaving variable has to be S3. So entering S1, leaving S3. Okay. And now row operations using this row, I will make this a 0, 0, 0, 1. Okay. Any questions? You okay? Okay. So if you do this, so the row operations, and you can check this, the row operations for this is, so I can make this, so it's minus 1 by 3. So I'll do it half row 0 plus half of row 3 will give me the top row. So you can check that these row operations will be the right ones to do. Let me write it down. You can verify that these row operations will convert it to the form we want. Okay, and you can check this. And if you do this, you will get a tableau which looks like this. Because my variable that entered my basis was S1, so wherever S3 was, S1 will come there. So I'll have X1, X2, and S1. And it turns out actually this is the optimal tableau. 1, 2, 2. Okay. Okay. So where are we now? We are at the point X1 equal to 1 x2 equal to 2, okay? And at this point, s1, so s2 and s3 are 0. Where is this? S2 and S3 are 0. S3 is 0, S2 0. So we are at point B. So we have gone along this direction, along this feasible direction, and we have gone to point B. And it turns out this, in fact, is the optimal solution. How do I know this? I check at this point. So this is the point B. At point B, all my reduced costs are non-negative. C bar is completely non-negative. If my reduced cost vector is non-negative, then last time we showed that that's an optimal basic feasible solution. It's clearly feasible. We're always staying feasible. Okay. So point B is optimal. Okay. So x1 star is equal to 1, x2 star is 2, and from this you can find the slack variables. What is the cost of this? It's a negative of 7. So optimal cost, it's minus, so my objective is minus 3x1 minus 2x2, which is minus 3, minus 4, minus 7. That's negative of this. So everything works out basically. Okay, and we have converged. So in this method, we required 3 simplex iterations: 1, 2, 3. So using this approach, what we just did, we in 3 simplex iterations, we converged to the optimal solution. Okay, there was a total of 5, 1, 2, 3, 4, 5 basic feasible solutions in this problem. We started at 1. I mean, if we were lucky, we would have started at B, but we did not. This is not what happened. Okay, so we picked the most easy basic feasible solution, and in 3 iterations, we converged. Okay. Okay, any questions with the algorithmic steps that we followed? Was there anything which was unclear in the steps? Okay, so let me ask you a question. So suppose instead of choosing x1 to enter the basis, suppose at the starting point, at the starting tableau, I had minus 3 and minus 2. I chose minus 3, x1 to enter. Suppose I had chosen x2 to enter my basis. How do you think I would have moved on this simplex method? Sorry? You will move to A, exactly. So you will move, actually, if we had started, so if I just take this figure, let me just move this to the other. Good. So I think you, so if we, so when we, at the starting tableau, when we let x1 enter, and then we require 3 simplex iterations. But instead, if I had let x2 enter at the starting tableau, which I could have, because my reduced cost in my starting tableau, my reduced cost for x2 was minus 2. I could have also chosen that. Then as identified, I will increase x2. X2 was initially 0, non-basic. I'm going to increase x2. So in that case, so in this case, if I went O, E, D, B, in that case, I would have gone O, A, B. And actually, I would have converged in 2 iterations. Okay. So it might have appeared to you at the start that a smaller reduced cost is a better thing, but it depends how much you can move in that direction. And it depends on, it's not obvious that choosing the smallest reduced cost will give you the best way to get to the optimal solution. Okay. This is not an obvious thing. In fact, it's not true. Okay. Okay. So this is, but that is an all. So there are alternative pathways here which can also make you converge. Okay. One very, very important thing in simplex is, as you can see, we are going along the boundary. These are called the faces. Okay. There are some algorithms which I will cover in the second half where you can go to the interior of the feasible region. We won't do that at this point, but the simplex method goes along the boundaries. Okay. Okay. Good. Any questions with the simplex method? Okay, I will explain why the method works. But before we do that, any questions online on the method or? So you should be wondering, why these row operations are doing the right thing. Why is it converging? Why is it doing what we expect it to do? So we'll talk about that next. But before we do that, I want to just mention I want to make a couple of observations which are useful. There is a lot of information, okay, a lot of information stored in the simplex tableau. Okay. So, so let's think about, uh, let's look at this tableau. Okay. If you look at this tableau, you will see that, okay, remember there are three, M is three. So there are three basic variables in this problem. You will observe that in this tableau, there's a 1, 0, 0, 0, 1, 0, 0, 0, 1, which corresponds to my original basic variables. There's an identity matrix. Go to the next point, E. My basic variables are x1, s2, s3. Look at the columns. 1, 0, 0, 0, 1, 0, 0, 0, 1. Identity is hidden. Okay. X1, X2, S3, 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay. So the first thing which should be quite clear to see is in the tableau. So remember what my tableau is doing. My simplex tableau, at every step, there is a B inverse times A, right? In the right hand side. But A consists of my basic variables and my non-basic variables, which means that wherever my basic variables are there in that matrix, I will get B inverse B, which is the identity, and the remaining will be B inverse N. Okay. So the columns of the tableau corresponding to basic variables will always be identity. This always has to be true. Okay. And one very important thing is the tableau is keeping track of B inverse A. It's not keeping track of B. Okay. It's not keeping track of the basis matrix. I mean, you can identify the basis matrix from the basic variables, but it is storing B inverse A. Okay. Okay. Now it turns out you can also identify the basis matrix. Okay. And I'll just, actually, the basis matrix inverse, actually. Okay. Okay. Is that clear? Okay. Okay. Now the next thing you can observe is in the tableau is suppose my identity, my A matrix had a form where there was some components and there was an identity matrix at the start. Okay. How does this happen? For example, if you have slack variables. Okay. So for example, if you have slack variables in your original LP, my original LP had less than equal to, I added slack variables. So I got an identity along this at the starting A matrix. My A matrix here is 1, minus 1, 1, 0, 0, 2, 1, 0, 1, 0, 1, 0, 1, 0, 0, 1, right? So this A matrix has a identity. If it has, suppose A is of this type, it may not always be the case. Then if you think about what B inverse A is, there'll be a B inverse times this part times B inverse identity, which is exactly B inverse. Okay. So if you look at the columns of the tableau where the original identity matrix in A was, it will actually automatically tell you what B inverse is. Okay. Remember, B is very easy to find. I give you the basic variables. I just take the columns corresponding to the A. I take the A matrix and I just picked up the columns corresponding to my basic variables. That's B. But we are automatically getting B inverse without inverting a matrix. We never inverted a matrix here at any step. Okay, I never did. I mean, I did row operations, of course. Okay, but I never went and exhaustively inverted a matrix. Okay, so for example, let's take this tableau. Where is B inverse? Okay, so in this problem, at the starting tableau, my A, my identity is here. So B inverse times this columns will be B inverse, which is just the identity itself. Okay, so here at this point, B inverse is what? It's the columns. So originally, so my point is wherever your original identity matrix in A is, that's where B inverse is stored. So for this, B inverse is simply these three. It's identity. The inverse of identity is identity. Okay. Let's take point E. X1, S2, and S3, the inverse of this, the basis matrix will be these three columns. This is going to be B inverse for this basis matrix. You can go and verify it. Okay, take the columns of A matrix corresponding to X1, S2, and S3. Take that matrix, invert it out. Okay, do whatever, use any linear algebra package or do it by hand. It's 3 by 3. You can do it if you want. You will find that this is exactly B inverse. Similarly, B inverse for this basis matrix is stored in these three columns. Okay. And lastly, for the optimal tableau, B inverse is stored here. Okay. So one of the beauties here is that B inverse can be identified by looking at the columns. So columns in Tableau corresponding to the identity matrix in A, if it is there. Okay. Sometimes A may not have it, but if it is there, you can find it. Okay. Of course, if I give you a basis matrix, I can always do find an inverse of a matrix. That's not a very hard operation to do. It's roughly if there's a m by m matrix, it's roughly m cubed operations. Okay. But it's automatically is given to you in this Tableau. Okay, so Tableau actually stores a lot of useful information without you even knowing it. Okay. Okay. Good. Any questions with that? Was it clear? It's clear what the basis matrix is, what the basis inverse is. Is that clear? Okay. So what we'll do next is I will discuss. Okay. Any questions before? For what to be zero? Can the ratio be zero? It if the so a point is what happens if theta star is zero? It can be zero. When can that happen? When it's a degenerate basic feasible solution. I'll come back to this. If some of the basic variables here are zero, theta star is zero divided by something, you'll get zero, which means you're on a degenerate solution, which is what we discussed. You can degenerate basic feasible solutions are problems where you change the basic variables, yet you stay at the same geometric point. So that can be an issue in LPs. And so that's a good point. You can get theta star to be zero when you, at a degenerate point, and we will discuss that. Yeah. Yeah. But this can happen. So this is why in LP developments, Simplex, you have to deal with these issues basically, the actual implementations. Good. Okay. Okay. Any other questions about the method? I want to discuss next why the row operations make sense. But before I do that, I just want to ensure that there's no questions about the algorithm itself per se. Okay. Okay. Yeah. Okay. Then let's. Okay. So what I want to do next is talk a little bit about uh, row operations. I mean, what is the link between these row operations that we are doing and the Tableau? Like, how are they related? Exactly, what are we doing actually with these row operations? Okay. Okay. So I want to make this connection so that it makes sense to you that when you're doing this row operations, actually every time the Tableau is capturing what it is expected to capture. Okay. So just remember, my Tableau I clinged is of this type. Okay. At any step, this is my Tableau. Okay. So at a current basic feasible solution with the basis matrix B, This is my tableau. If I decide to change my basis, so I move to a new basic feasible solution, I require this tableau to be correctly updated. So the next step, when I go from B to B bar, a new tableau, let's call this B bar, okay? It should be the case that this tableau is actually doing this. I mean, we never explicitly created this all this matrix inverses and so on. So we have to ensure somehow that in the operations that we're doing, when we go from B old BFS to a new BFS, it's automatically updating it in the correct way. Okay, and we did this only to row operations basically. Okay, so let's try to figure out why this is doing the right thing. Okay, okay. So firstly, just a quick reminder that row operations are basically nothing but, so what's a row operation? You can think about it like pre-multiplying by a matrix. Okay. So for example, suppose I'm doing an operation like this, row one, I'm doing row one, let's say row one plus, let's say 4 times row two. What am I doing? I've got a matrix, okay, to which I'm applying a row, I'm doing a matrix I'm doing a pre-multiplying. So this is my matrix, this is my tableau to which I'm doing a pre-multiplication operation. Pre-multiplying by matrix Q, which is rectangle, which is square. What is this matrix going to be? This is going to be 1400. Let's say this has got 4 rows. If I'm doing a row operation of this type, right? This is exactly what a row operation is. It's pre-multiplying by a matrix. Okay. So this is row one plus 4 times row two. Row two stays the same. Row three stays the same. Row four stays the same. So if I do multiple row operations, I'm just pre-multiplying by a sequence of these matrices. That's what row operations mean. Okay. Okay. So this is just a reminder. Okay. Okay. So now what did we do in our row operations? In my row operations, I tried to make this column. Okay. I chose, so let's say we are at B, at a basic feasible solution B. We decide to let xj enter the basis. So this is the non-basic variable which I'm deciding to bring into my basis. Okay. So So what is happening every time? Every time in Simplex, one basic variable is entering my basis and one basic variable is changing, is going out. So my basis matrix, there's a swap of one entry. There's one vector basically. Okay. So my B bar, a new basis matrix, is B bar. Okay. So you should be able to, I mean, it's quite clear that I have this basis matrix. The column corresponding to xj comes out of my basis basically. It's sorry, xj comes into my basis, and the leading variable, which is the variable that I did for my pivot row, comes out of the basis. So I've got a current basis matrix. I decide to take out a base variable from my basis and bring a variable into my basis. So this column corresponding to the AJ column corresponding to the XJ variable enters my basis, and the column corresponding to my leaving variable leaves the basis. Okay. So that's my new basis matrix B bar. Okay. So clearly B inverse B is identity. This is obvious. Okay. What is B inverse B bar? Okay. What's the difference between B and B bar? There's one column which is different. In this B bar matrix, all the columns are the same as the original basis matrix except one column. The new column is this corresponding to AJ, okay, which entered. So if I look at what this product will be, there will be a lot of identity columns of there'll be a lot of identity unit vectors, except the jth part, where now I will have this B inverse AJ. So there'll be one column which is B inverse times AJ, because in this B bar, this xj variable entered my basis. So there's one column here, which will be B inverse AJ. Everything else will be just an identity matrix. Okay. So it's almost an identity matrix, but for one column. Is that clear? Okay. And this is nothing but, just remember, this is just nothing but the basis variable, the basis vector direction, the negative of it, basically. Okay. 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 Now what did we do? We applied row operations. Okay. So originally we did, I'm going to just move to my next slide. So my old Tableau as B inverse, there's a B and there's a A. So B inverse B and B inverse A, my old Tableau as. Okay. My new Tableau, I did row operations. How did I do my row operations? So my row operations is nothing but pre-multiplying by a set of matrices Q. Okay. So Q times B inverse B A. How is this done? How is Q chosen? Where? What should Q satisfy? Where Q is such that, what did we do? We had originally, sorry, in my row operations, every time what I did was I tried to make this a unit vector 0, 1, 0. So I made it I converted this back to an identity matrix basically. I have this Q, I took this matrix, but I made this a 0, 0, 0, 1, 0, 0, 0. So I applied basically a matrix so that this became identity. That's what my row operations was doing. I was making it 0, 0, 0. The pivot entry became a 1, everything else stayed a 0. So I'm converted it back to an identity. Q is such that Q times, if you look at this B inverse B bar, became identity. This is exactly what we did with the row operations. These were our row operations. You agree or? Okay. Then what does this mean? Then, because of course these basis matrices are invertible, so Q B inverse has to be B bar inverse identity, which is just nothing but B bar inverse. So what has my new Tableau become? My new Tableau, at least forget the top row as yet, the cost vector, but everything below Q B inverse is nothing but B bar inverse. So it's B bar inverse B A, which is what we want. We want to ensure that when I do my row operations, it's B inverse B, B inverse A. I want it to become B bar inverse B, B bar inverse A. By doing my row operations, I did it. Okay. So there is a rational, I mean, obviously there should be a rational, but there's a clear mathematical argument for why these row operations are doing the right matrix inverse. I mean, it's keeping track of B inverse A appropriately as we change the basis. Okay. Okay. Note nowhere we actually explicitly compute. I mean, we never inverted matrices explicitly anywhere. Okay. At any step. Okay. Okay. Is that clear, or do I need to go through that argument one more time? Okay. Um, so we'll talk about the top row next. Shall we do the top row, or you want a break? We can come back and discuss top row. If you want some time to assimilate, we can take a 5 minute break, or we can talk about how the top row is also changed appropriately. We'll do top row. Okay, so let's talk about how the top row. Okay, so this part we have discussed. So let's now talk about the top row, how it is why the changes are happening appropriately. Okay, so what's the top row keeping? So okay, so row 0. So this is for row 1 up to row m. So for row 0, what is row 0? The top row. It keeps track of minus CB transpose B inverse B and the reduced cost vector, which is C transpose minus CB transpose B inverse A. Okay. So remember that this is just a scalar, and this is a 1 into n vector. Okay, this is a top row, row 0. Okay. Okay, this is for my old BFS. Okay, okay. I'm going to just rewrite this in a slightly different form. I'm just going to take the, I'm just going to split this up. Okay, zero. So think of this as zero C transpose. Okay, minus there's a CB transpose B inverse B and A. Okay, so I'm just rewriting this. This is 1 into 1. This is 1 into N. This is 1 into M. M into M. So this is 1 into M. This is M into N. Sorry, it's M into N plus 1, which should be correct. Because this is 1 into, I mean, this entire thing is 1 into N plus 1, right? The entire thing is 1 into N plus 1, right? So this is 1 into M and M into N plus 1. So it's basically there's a cost and then there are reduced costs for N variables. So N plus 1 entries in the top here. So I mean, I'm just taking the zero out, the C transpose out, the CB transpose B inverse, I'm keeping together. I'm just rewriting it, okay, in vector form. Okay. Now you can think about this as nothing but zero C transpose. This is Q times some BA. Okay, so this is some linear combination. Okay, some linear combination of the rows of B and A because I'm pre-multiplying by some matrix CB transpose B inverse. So the top row is basically keeping track of the costs, zero, and the original costs plus some linear combination of the rows of B and A. Okay, that linear combination is given by this, right? I'm pre-multiplying a matrix is just row operations. Okay, okay. So it's taking a linear combination of this basically. Okay, okay, fine. Now let's look at what happens with the with my. So what did we do? Let's say xj entered my basis. Why did xj enter my basis? There's a negative value here. There was a positive value here. We decided to use xj to enter my basis. Okay. So this is the entering variable. Something left, leaving variable. Okay. And all the remaining basic variables, there was, uh, remember the remaining, so this is a non-basic variable. This enters my basis. All the remaining basic variables, so wherever there's a basic variables will always have a zero reduced cost. Okay. And there will be some entries here. Okay. Whatever. There'll be some entries here basically. Okay. Okay. Uh, okay. Now what did we do with our, so suppose xj enters and let's say xi leaves the basis. Xj enters basis and xi leaves basis. Okay. So after the row operations, what happened to top row? We'll see what happened to top row. Okay. We hope that our top row, the new row naught, okay, is of the type zero. So we are doing row operations, right? So there's zero and C transpose. Sorry. Minus, we are doing row operations using the B and A. So it's some P transpose. So we are creating a new linear combination. So there's an original linear combination, which is CB transpose B inverse. There's there's an original linear combination of the rows of B and A. Okay, using the old basis matrix. This new linear combination that we are creating, the new linear combination, what does this have to satisfy? We made the reduced cost. So this the we made this thing go to zero basically. Okay. So this new value in this new basis, when I did my shift, I made this zero. So Cj, the jth entry, Cj minus P transpose the Aj value has to go to zero. I make this number go to zero with my operations. Okay. Okay. For every other, for other basic variables, Okay. Remember, my basic variables will have entries like um, the cost for my basic variables. There'll be a CB transpose the for all the remaining basic variables. Okay, whichever the old ones which were there. Okay, the costs there. Sorry, all the remaining basic variables CB transpose. So this cost minus P transpose the basic variables, those were all became basically zero. Okay, so we don't change. So for the remaining basic variables, essentially those values remain at zero, the basic variable costs. Okay, because basic variables will always have a zero reduced cost. Okay, which means that this P transpose is CB bar transpose B bar inverse. Okay, so my new rho naught is simply zero C transpose minus C bar transpose B bar inverse BA. Okay, which is nothing but minus C bar CB bar transpose B bar inverse B. So the top row is changed in the correctly. Okay, so what we wanted, so just maybe I went a bit quickly here, but let me just. So my top row is originally stored in this form. It's some linear combination of the rows of B and A using the basis matrix B, the original basis matrix. I want to argue that after doing my row operation, it becomes the another linear combination of rows, except now I'm using the new basis matrix inverse. P bar has to show up here. Okay, that's what I want to argue with the row operation. How did this happen? We made the row operation so that this my costs here, my reduced cost, my reduced costs of my basic variables were kept at zero for this basis matrix B bar. Okay, so this P transpose has to satisfy this condition, which means that you will get the right linear combination. Okay. Okay. So the point is that all the if you work through the linear algebra, all the steps, it's the simplex tableau is keeping track of the right numbers and is making the updates correctly. Okay. So now what we'll do is after the break, I will come back and I will talk about all the different situations, things like unbounded optimal solution, degenerate solutions, multiple optimum. What if you don't have a starting BFS? What do you do? How all those things can be accounted for by appropriately looking at the simplex table. Okay. So we have the basic idea. You should be able to now run the basic simplex method. Okay. Okay. Let's take a break. It's 11:05. We'll start at 11:10. Okay. If you've got questions online, you can ask me. Yeah. Yeah. No, 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 not chronological stuff, just the current. Because I heard that you have this thing. Yeah. I voted from the shares in. Shares. Yeah, it was like. Or for each yeah. Be yeah. That's high to some kind of chewy candy, but not chewy gum. Okay. think I got, I think most of you sent me by email. So yeah, yeah, it's fine. By the way, next Friday there's a, I don't know if you guys know about it. There's a, I mean, there's a workshop in SMU. Do you know this? Or there's a workshop in SMU. Do you know about this or no? No. Okay. So there is a, it may not be of interest to all of you, but last year they started this thing called the OR Day, Operations Research Day. It happens in some countries, like in US and stuff. But anyway, so last year they held it at NUS. So this year it's in SMU. So what happens is people in NUS, NTU, SMU, SUTE, some faculty members and some students present their research and give talks. So I will share it with you guys. It's on Friday, next Friday. So it's our class day. I will share it. I know not all of you might work in OR and different areas, but if you want to understand what type of things people are doing in their area, in this area of research, it should be a reasonable workshop to go to. I think you'll get a good idea. Maybe one day you guys are also present there or that posters there. So maybe we can, I'll share it with you. You can have a look at it. You can, I mean, you can check with the advisors if it's worthwhile to us. But I was just mentioning there's a workshop happening next week on Friday at SMU. They started something called a Singapore OR Day last year. I think it's happening every year now in a different university. It's appropriate for just to get an idea of what type of research people are working on. We get a sense. Yeah. Yeah. Okay. Uh, are there any questions online? I see a couple of you there. If you've got questions, you can ask me, or it's fine. If it's... Okay. So maybe we'll start then. So I guess uh, what I want to do for the next 45 minutes or so is just ensure that we just discuss all the other issues related to the simplex method, which are most critical, and sort of complete the discussion. Okay. Okay. So, uh, so we spoke about trying to trying to converge till we get all the reduced costs to be non-negative. Okay. Now, of course, we know in simplex we can have uh, unbounded optimal values. Okay. So how does the simplex method identify if an LP has an unbounded optimal value? How do you know this? Okay. Okay. So if you think of the simplex method, at some point in the in the iterations, let's say I come to a non-basic variable xj, so it's a non-basic variable where the reduced cost, so remember this top row as a reduced cost. Let's say the reduced cost here was a negative value. Okay, which means what? I want to increase xj. So I want to move in the direction where xj increases at a rate of 1. All the other all the other non-basic variables are at 0. And for the remaining basic variables, I'll find a direction given by this db, this direction vector. Okay. When we did the ratio test, we had, so suppose there exists some variable xj, there exists xj non-basic variable where the reduced cost is negative, okay, and the this corresponding B inverse AJ. So remember, this column is the B inverse AJ column in the tableau. if this column B inverse AJ has all the entries to be less than equal to 0. Okay, what does this mean? This is equivalent to saying the direction vector dB, which is minus B inverse AJ, is always non-negative. What does this mean? This means that I've identified a direction where the non-basic variable is increasing at a rate 1. All other non-basic variables are 0. And my basic variables, there's a direction to move them. So I can keep increasing in this direction. And my x plus theta d will always be non-negative. Then the optimal value of the LP will be minus infinity. Okay. So the moment you find a negative reduced cost in your tableau and the corresponding B inverse AJ as all values which are less than or equal to 0, then you are essentially identified that this LP is unbounded. Okay, because there's a direction in which the cost is decreasing and you can go arbitrarily in that direction by continuously increasing your non-basic variable value, that xj value. All other non-basic variables are 0, and the basic variable directions is given by this minus B inverse AJ. And because of this values being non-negative, non-positive, the direction vector is non-negative, so it satisfies the conditions basically. You can keep on x plus theta d will always be non-negative. Okay. Okay. So it is very easy to identify an unbounded optimal value in a simplex tableau. Okay. Okay. Any question with that? I won't do an example, but I think it should be clear. I mean, you can construct examples. I'm sure the book has some examples, but you can construct examples. Maybe some of your practice questions I will give you might have it. Okay. But basically, the idea should be clear. Okay. Okay. So let's go to a theorem now about convergence. Okay. So this theorem actually is about convergence of the simplex method. Okay. So suppose the standard form LP is feasible. Okay. Of course, suppose the standard form LP. So I want to start by talking about the convergence of simplex. Okay. So we need some assumptions for the start. We won't do the complete proof for general convergence. I'll tell you what the issues are, but at least this one is easy to understand. So suppose the standard form LP is feasible. Okay. And so we are making assumptions. And every basic feasible solution is non-degenerate. Then the simplex method will identify an optimal solution or identify LP is unbounded or identify optimal value is unbounded. So what is the claim? In finite number of iterations, and this basically means finite time also, because every operation here is a you're doing just row operations, so these are all simple operations. You can't cycle basically. Okay. 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 So that's the claim. Okay. So there are two assumptions here: standard form LP is feasible, and every basic feasible solution is non-degenerate. Okay. So I haven't told you as yet what to do if the LP is infeasible. We'll come back to that. But the problem is, but let's think about interesting problems that the LP is feasible and every basic feasible solution is non-degenerate. Okay. Okay. So why is this the case? Okay. So think about your standard form LP. Okay. My number of basic feasible solutions is bounded. There are m equalities and n non-negativity conditions. We have seen this bound. Number of basic feasible solutions is always upper bounded by n choose m. Okay. We have seen this bound n factorial by m factorial by n minus m factorial. Okay. So what happens in the simplex method? At the simplex method, so at every step, if Cj bar is less than 0 for some j, we will be able to move to a new point. Okay. Why is this the case? Because it's a non-degenerate LP. So this LP, no basic feasible solution is is no feasible point, no basic feasible point is degenerate, which means that there's some positive amount. It might be a very small amount, but you can move to a new point. Okay. So we will be able to be move to a new point such that so we'll be able to move to a new not only point, but actually you can move to a new basic feasible solution because every step you move to a new basic feasible solution such that the cost decreases. It decreases at a rate of Cj bar. If you go some amount of distance, you will decrease at this rate, theta times Cj bar. And Cj bar is negative, suppose it's negative, and theta star has to be a non-zero value. Okay. So you are moving to a new basic feasible solution such that the cost decreases. Okay. Since there are only a finite number of BFS, and the cost only decreases at each step. You will never revisit a BFS. You will never start at a BFS and come back to a BFS in the simplex method because the simplex method does not let you do it. Right? You will only choose negative reduced cost and get moving. Okay. You will never revisit a BFS and always decrease cost. Right? Or you'll identify as unbounded. Okay. So this implies that you can never get stuck and it'll terminate in finite time. So this implies you cannot get stuck. And in a finite number of iterations, in fact, this is a bound on the number of iterations. In the worst case, maybe you have to go through every basic feasible solution, but this implies you cannot get stuck and will converge in finite time. Okay. Is that clear? So there's some assumption here of non-degeneracy, which we require. Okay. But basically, hopefully the argument is clear. At every step, you're decreasing your objective function value. You have always some direction to go to. You can move to a new basic feasible solution. You don't have this degeneracy issue. So you will decrease. And because the number of basic feasible solutions, the number of optimal points is a finite number for LPs. You can restrict attention to only basic feasible solutions. You will converge in finite time. Okay. Now, if you think about each step of the simplex method, each iteration, okay, what are you doing in each iteration of the simplex method? You have this tableau which you are updating, right? Each iteration of the simplex method, what is the size of this? Roughly, I mean, if you're very precise, there's M here, there is one row here, there is one column here, and n columns here. When you do a row operation, every entry in this tableau is getting updated. It's basically what you take that number and you add or subtract something. Okay. So roughly each iteration of the simplex method requires order of m times n operations. Okay. By operations, I mean basic operations like addition, multiplication, and so on. Roughly size of order of mn. Okay. So if you multiply the number of iterations, the number of basic feasible solutions times the number of order of mn, that's roughly the number of steps you'll require, the number of operations you'll require rather. Okay. Okay. Is that clear? Okay. Now it turns out you can decrease this to order of m squared. Okay. Because if you think broadly, what happens what is really important to you is this B inverse matrix. You have to keep updating. This B inverse, ultimately, what's your optimal solution? B inverse B. So if you find this B inverse, if you can keep track of B inverse in the different steps, you're done actually. As long as I keep updating B inverse correctly, okay? So you can actually decrease order mn to order m squared using something called a revised simplex method, okay? Uh, using careful, I mean, I'm not going to go into this in this class, using careful bookkeeping, okay? Bookkeeping meaning you can be a bit more careful in the way you keep the tableau, you parts of it only you update and so on. You can do this. It's called the revised simplex method. You'll find it in the book. So for those of you who are very algorithmic, you can look at it if you're interested. But it's just, but if m, typically what m is smaller than n in a standard form LP. So if n is much larger than m, this can be an advantage. Okay, because n, if n is much bigger, you don't have to, you can, instead of having order mn steps every time, you can do order m squared operations every time. Okay, so that is a method. I won't go into it for this class. It's but you can read it on your own in the book if you want. Okay, it comes under the name of revised simplex method. There is some, you just maintain B inverse basically at every step. Okay, okay, okay. So is this broadly clear? Yeah. Okay. So let's then talk about what degeneracy causes. Okay. Okay. So what is the challenge in degeneracy? Okay, we are not going to be able to in this course or in this class, at least I can't deal with all the the proofs here, but I want to just tell you what can happen and what is the solution for this problem. Okay, okay. So the key challenge what degeneracy causes is it can cause cycling in the simplex method. Okay, which means that you are at a point. Okay, you move to a, so you try to change, okay, maybe you go to some other point, you try to change, okay, basis, okay, you move, you keep doing this, and then you come back to the same, so you change basis, change basis, change basis, you're at the same point. Ultimately you come back to the same basic variables and you're not moved out. So it's like a cycling, right? You change, so I won't do an example. I'm just going to, you, I want you to just try this out on your own. This is from the textbook. Okay, so you can look at the textbook example. It will take time for us to go through all the steps. Okay, but I'll tell you, I'll just give you the idea of the example. In the textbook, it's on page 104. So here is an LP. Okay, you can create examples. Okay, I'm going to give you a basic feasible solution at a particular, for a particular LP. Okay. Again, this example is in the book, so you can read the book if you want carefully for the for details on the example. Okay. So remember where my basic variables are. There's identity. Let's say, so that's a basic feasible solution, standard form LP. Okay. There's a negative of the cost, there's a reduced cost. Okay. Now in the simplex method, we have choices of the entering and the exiting variable. Of course, the entering variable has to have negative reduced cost. The exiting variable has to have the minimum, attain the minimum in the minimum ratio test. What is the choices? If I've got more than one variable with a negative reduced cost, I have to choose which one to enter. If I've got multiple variables which attain the minimum in the minimum ratio test, I have to choose which one has to leave. Okay. So suppose you use the following rules. So suppose we use the pivot rule. One, the entering variable is the most negative reduced cost. Okay. So in this example, I've got two reduced costs which are negative. The most negative reduced cost among these two is minus 3/4. So that's my rule. When I code my simplex, I say compute the reduced cost, whichever is most negative, I will let that enter my basis. So in this case, x1 will enter the basis. Okay. And my exiting variable rule is, so my leaving variable is smallest index variable that attains the minimum in the ratio test. Okay. So what I mean by this is, suppose I have two different variables. Okay. So in this problem, so in this example, that's a degenerate solution, right? Why is it degenerate? Two of my basic variables are zero. So firstly, observe that this is degenerate. I should have actually mentioned that. Okay. Degenerate. Basic variables are zero. What should I do when I do my minimum ratio test? 0 divided by 1 by 4, 0 divided by half. So 0. So I've got two choices. X5 can leave my variable, or X5 can leave my basis, or X6. My rule I'm going to use when I code my algorithm is the one with the lower subscript, X5. So if I use this rule, my leaving variable will be X5 leaves the basis. Okay. Okay. Now you implement the simplex method. So X1 will now enter, X5 will leave. Okay. So if you implement the simplex method for this example, okay, and I will let you try this on your at your own time. Okay. So in this example, X1 will enter, X5 will leave. X1 enters, X5 leaves. Okay. Now you can repeat this. So you will get a new tableau. Okay. Now you can check at your own time that the next step will be X2 will enter, X6 will leave, X3 will enter, X1 will leave. Okay. You can only do this by doing the actual steps. Okay. I don't want to do it in the class. It will take time. Okay. You can try this at your own time. You keep repeating till you come back to the original tableau where again you get X1 and X5, X1 entering and X5 leaving. So what happens is after six iterations, 1, 2, 3, 4, 5, 6, you can verify after six iterations, you get back to the same tableau. If you follow this rule for this example, okay, you come back to the same step where X1 and X5 will, X1 enters, X5 leaves because you've got back to your same tableau. Okay. Now again, you have to do the example to check this. Okay. Go through the steps. But what's happening is you add a degenerate solution, and with these rules, you keep on changing your basic variables till you come back to the same tableau and you have not moved geometrically out of the point. And observe that reduced costs here are negative. So you're not optimal. Okay. So it's not that you're at an optimal degenerate basic feasible solution. You're at a point where it's non optimal and you're not able to get out of the point with your choice of your pivot rules. Okay. So what happened is for a long time, people were trying to identify rules, pivot rules, which will ensure this cannot happen. You cannot get cycling. Okay. It may, I mean, you might be lucky and it may not happen, but there are examples or there are worst case instances where cycling can happen. So the rule that turns out to always work is, again, we will not do the proof in this class. It's going to take too much time. There's a rule called Bland's rule named after this person. So what is Bland's rule? It says entering variable is smallest index variable for which CJ bar is negative. Okay. And there are a lot of pivot rules you can think about. You can think about computing, taking the smallest reduced cost, taking the index with the smallest, like the smallest index for which the reduced cost is negative, or computing theta star times CJ bar and figuring out which one is the smallest value and so on. So there are many rules which people have proposed. It turns out Bland's rule, where you choose the smallest index for the entering variable and similarly smallest index variable that attains minimum in ratio test. If you use these two choices of rules for entering and exiting variables, then it turns out uh, cycling never happens, even with, I mean, cycling never happens with degenerate. I mean, okay, it'll never happen anyway with non-degenerate. Cycling never happens with any LP that has degenerate basic feasible solution. Okay. And so what this means is simplex will converge in finite time even for degenerate LPs. Okay. So previously we spoke about simplex converging in finite time for non-degenerate LPs, where every basic feasible solution is non-degenerate. If you have degeneracy, you have to be more careful with your entering and exiting variables. You need some rules, you need more careful analysis. Okay. So this is where algorithms, people who study optimization have thought about this carefully, and this is developed many years back now. They've looked at it and they've studied it and they've tested it out and they have proved it. Okay, we won't do this proof here. We won't have time for it. Okay, okay. But the point is, simplex. What this says is simplex method converges in finite time under appropriate pivot rules for essentially any LP. Right? That's what it says. Previously, we said for non-degeneracy, for degeneracy with some conditions on the pivot rules, not every pivot rule, but for some pivot rules, you'll get it. So by some algorithmic choices on the pivot rules, you will get convergence in finite time. You won't have cycling. Okay. Okay. Any questions with this broadly? I won't do this. You can try this out on your own. This counter example. There are other counter examples out there. Okay. Sorry. Other type of cyclings. Uh, Not in the simplex method. So okay. Of course, it doesn't mean that. So I can't think of in this example, not in the simplex method. Maybe other algorithms, maybe, but not in this algorithm. I can't think of any other cycling. What can happen is, of course, you might be at a degenerate BFS, and you might. It's not that you're always going to be unlucky. You might be. There are times when you might change, and you might exit it also, degenerate. But I don't think there's any other type of cycling for this example. Like not in simplex, because in simplex your cost will decrease. So I don't think it's going to happen. Yeah. 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 Okay, good. Uh, okay, so next, okay, so let's talk about multiple optimum. Okay, so this is maybe so multiple optimum solutions. How do you find this? Okay, I'm just going to tell you the idea. Okay, so how do you find it? Identify if something is a multiple optimum. Okay, so essentially, okay, this is not critical. Okay, we don't have to. I mean, when you're solving an LP, I want to find an optimal solution. Whether there are multiple optimum is not really the question that we are starting off. It's maybe something useful for you to know. There might be more than one solution which is optimum. But when I say solve an LP, you have to find me an optimal solution. But it turns out from the tableau, you can identify if there are multiple optimum solutions. How do you do this? Okay. So I'll give you an example. So let's say this is a tableau. So this is why Tableau has so much useful information. So here's an example for a Tableau. Again, this is for an LP. The precise LP is not important. X1, X2. Okay. So this Tableau, this is an optimal Tableau. Why? Clearly, it's a basic feasible solution. And all my reduced costs here are non-negative. So it's optimal. So I've solved the problem. Okay. So clearly, X1 equal to 1, 2, X2 equal to 2, X3 equal to 0, X4 equal to 1, X5 equal to 2, X6 equal to 1, X7 equal to 2, X8 equal to 1, X9 equal to 1, X10 equal to 1, X11 equal to 1, X12 equal to 1, X13 equal to 1, X14 equal to 1, X15 equal to 1, X16 equal to 1, X17 equal to 1, X18 equal to 1, X19 equal to 1, X20 equal to 1, X21 equal to 1, X22 equal to 1, X23 equal to 1, X24 equal to 1, X25 equal to 1, X26 equal to 1, X27 equal to 1, X28 equal to 1, X29 equal to 1, X30 equal to 1, X31 equal to 1, X32 equal to 1, X33 equal to 1, X34 equal to 1, X35 equal to 1, X36 equal to 1, X37 x4 and x5 equal to, so x3, x4, and x5 equal to 0 is optimal. Okay. And the cost is obviously -6. Okay. Now in this tableau, so remember what's my tableau requirement? I require reduced cost to be non-negative. If I have, and obviously my basic variables will always have a zero reduced cost. If I have a non-basic variable which are with a zero reduced cost. So if you look at my non-basic variables are x3, x4, x5. Two of them have a positive reduced cost. But x3 is a variable, x3 is non-basic, and C3 bar is 0. So I've got a zero reduced cost and it's non-basic. Suppose I let x3 enter my basis. I can still do the row operations. I can force it. Suppose we let x3 enter the basis. Suppose x3 enters basis. Okay. Reduce cost is 0, which means that by doing this, my cost is not going to change. Okay, in this direction. But I can do it, and I can do my minimum ratio test 2 by 1 by 4, 2 by 1 by 2. So minimum ratio test will say this should be the leaving variable. X1 leaves. Then x2 will leave. Okay. And you can do your row operation to make this 0, 0, 1. Okay. If you write the new tableau, again, you can do the row operations on your own, I assume. You will get x1 now, x3 has entered my basis. I get 1, 4, 1, 0. Okay. So I've now come to a new point where x1 now is 1 and x3 is 4. Okay. So x1 is 1, x3 is 4, x2, x4, and x5 are 0. What's the cost? Also -6. So we have got two basic feasible solutions. They are non-negative. Two basic feasible solutions where the reduced cost, because my reduced cost of my non-basic variable was 0, you actually identify multiple optimal solutions. So when you're solving a simplex problem and at the optimal tableau, you're finding non-basic variables with 0 reduced costs, is generally an indication that there are multiple optimum solutions. Okay. So essentially, non-basic variables with 0 reduced cost. Okay. Of course, you have to be able to move in that direction. Okay. I mean, you might be able to create some crazy cases, but I'm able to change. I'm able to move in this direction. Okay. I'm able to bring x3 into my basis, and I'm able to move in that direction by some amount and go to a new point. And because my reduced cost is 0, my objective function does not change, basically. So I'm still optimal. And I move to a new point. Now it turns out any convex combination of these 2 points will also be optimal. Okay, that's just true for LPs. Okay, so I've got two basic feasible solutions which are optimal. Every convex combination will also be optimal. Okay, so anyway, it's easy to identify multiple optimum solutions by looking at reduced cost of non-basic variables. If they are 0, it indicates, and you should be able to move in that direction. Okay. Okay. So again, this is why I said that LP is a lot of things, information is stored in the tableau, basically. Okay. Okay. Now there is essentially one important question that we have not dealt with, which we have to deal with, which is finding the initial. So the thing that we have not done as yet is finding initial basic feasible solution and testing infeasibility. Okay. So one important question is that when you're solving LPs, because LPs can be given in any form, it might be given with equalities, inequalities, a combination of them, non-negativities, and so on. Of course, I know I can always convert it to this form. Okay. But if I give you an arbitrary LP, besides being, it is possible that this LP is infeasible itself. This is possible. It's a complete possibility. Even if it is feasible, I should be able to find a starting basic feasible solution, which I've sort of got away so far because so far in this example, in the example we saw today, it was very easy to figure out a starting basic feasible solution. I've gone too far. It was very easy to find a static basic feasible solution. I had a lot of slack variables and my right hand side was non-negative. So all I did was I set all my slack variables equal to be this number and my original variables were zero. So when I have problems of this type, so the easy case is when? So easy case, which is what we have done so far, is this case. Suppose my LP is of this type where B is greater than equal to 0. Suppose this was my original LP I wanted to solve. All I did was I wrote this as minimum C transpose X subject to AX plus S equal to B, X non-negative, S non-negative, starting BFS, non-basic variables are X, basic variables are B. This is an easy case. It's very easy to read a BFS directly from this problem. The problem is not every LP is given in this form. LPs might be given in this form. So I'll give you, so we'll take an example. Suppose my LP was not in this form. Suppose this is my example. Suppose I wanted to minimize minus x1 minus x2. Of course, I'm keeping the example fairly simple. Okay. So here's an example where it is not exactly of this type where I can write it as ax less than equal to b where b is non-negative. Okay, this is a subclass of LPs. Okay, I cannot write every LP in this type where b is non-negative. This is not true. Okay, I can write every LP in standard form. Okay, so for example, this is an LP, right? It's got linear equality, inequality constraints, but it doesn't. If I make this less than equal to, it's a negative value. Okay, so it's not in the form where the even if I convert this to standard form, even if I convert this to standard form, it's not a priori clear how to identify the identity matrix here. It's not there a priori. Okay. I mean, this is a simple example. Maybe with a bit of work, you can find a basic feasible solution. But imagine a problem with many, many variables, many, many constraints. Because ultimately, we want an approach that works for any LP. Okay. So what you need to do, so there are a couple of ways to do this. The most common way, in fact, this is probably the most popular way, is what's called the two-phase method. Okay. So this idea is actually a very elegant idea. You convert, you have two steps, two phases. Okay. In fact, you use LPs itself, linear programs itself, to find a feasible solution. Okay. So what are we doing? Okay. So we are going to assume, again, it's a standard form LP. And we can assume without loss of generality, B is non-negative, right? I can always write an LP in standard form. Okay. And if B was negative, I would just take that equality constraint and multiply by -1, right? So this is there is no loss of generality in assuming this form. Okay. So this is perfectly fine. We can always do this. Like in this example, it's automatically true. But suppose it was not true, I would have just, suppose for some reason, suppose this number was negative. I would have just multiplied throughout by -1 into this inequality, right? Into this equality. Okay. So there's no loss of generality in this. Okay. Okay. The problem is I don't know immediately what's a basic feasible solution for this problem in this form. Okay. So phase one, what it does is add auxiliary variables. Auxiliary or what are called artificial variables. Variables which are not there in the problem, but bring them in. Okay. How do you do this? So you basically suppose you have m equality and n non-negative variables. You solve the following problem: minimize summation I going from 1 up to m y I subject to ax plus y equal to b, x non-negative, y non-negative. Okay. Let's call this LP star. Okay. This LP is different to the original LP. That the original objective function involved something C. I've forgotten it. I don't care about it. My objective function is now the sum of yi variables. To every constraint here, I'm adding a new variable. For one constraint, there's one variable. Because I've got m equality constraints, I've got m new variables. So I'm keeping A same, B same. I'm just adding a set of non-negative variables to the left-hand side. Okay. Okay. Now for this phase, for this LP, a BFS is easy to find. Okay. So starting BFS for star for this problem is easy. What's it? Put x equal to 0, set y equal to b, and y is non-negative. So, I'm sorry, b is non-negative. So y has to be non-negative. So it's a basic feasible solution for this problem, right? So it's an easy basic feasible solution for this problem. Now, what do I want to do? I actually want to find a basic feasible solution for this LP, for the feasible points, right? If I was to solve this problem, suppose my LP was feasible, the original LP. If this LP was feasible, that means there is some AX equal to B, where X is non-negative. Because my Y variables are non-negative, all my yi values should go to 0. My optimal value has to be 0. Okay. So use simplex method to solve phase 1 to optimality. So you create the reduced costs, check it is non-negative, and you solve it to optimality. And check what the optimal solution for this LP is, for this star LP is. Okay. Okay. So what can happen? At optimality, if all yi star are 0, then we know that the LP has to be feasible, because if yi is all 0, ax has to be equal to b, and x is non-negative. We are ensuring this. Then original LP is feasible. But if some yi star is strictly positive, then original LP is infeasible, because you're solving it to optimality, this LP, right? I'm trying to make all my yi's are non-negative variables. My best solution is when all yi's are 0. So find me an x in the set ax equal to b, x non-negative, and make all the yi's go to 0. But if I cannot do this, that means there does not exist any solution to ax equal to b, x non-negative. So by solving this LP to optimality, if I find that all the yi's are 0, the LP is feasible, the original problem. Otherwise, it's infeasible. Now what I do is, if it is infeasible, of course, you stop. You report it's infeasible. Otherwise, you go to phase 2. Suppose all yi's are 0. Now so if all yi star are 0 in phase 1, then you essentially start with the basic feasible solution using only the x variables. Okay. But now you solve it for the original. Now you use the original cost function. Okay. And solve original LP starting at this BFS. Okay. Now you expect all the yi's to be 0. So if all the yi's are 0, in general, you would expect them to be all be non-basic variables. So you just, so all the x variables will be the basic variables. So you take the x variables, the columns in the tableau for the x variables and take them in. Now it can happen that sometimes some of the y variables might be zero and it might be a degenerate optimal solution. So then you'll have to drive it out of the basis artificially. So there are some steps there, but they're not, but the basic idea should be clear. Okay. So I'll show you an example just to illustrate this. Is the idea clear or is it not clear? Not clear. Okay. Which is not clear? Phase one or phase two or both? Phase two. Okay. So let's do an example. Maybe the example will help. Okay. Okay, let's just do an example and we'll try to end with that. I just want to make a couple of points after that. We'll end. Okay. So here's an example. I won't do all the steps. Okay, but I will show you the example. Okay. So minimize minus x1. I'm going to keep it simple. Okay. The example. Okay. Okay. So here is an LP where I don't have immediately an identity matrix floating about immediately. Okay. If you see immediately, you can't see a 1001. Okay. Okay. So what will phase one do? Add auxiliary variables. So it's going to solve the following problem. Minimize y1 plus y2. My right hand side are positive. 2x1 minus x2 plus y1 equal to 1 equal to 5. And I've got now x1, x2, s1, y1, y2, non-negative. So here my problem, two equality constraints, three variables. Here I've got two equality constraints, five variables. Sorry, five variables. Why five? I added two artificial variables, y1, y2. Okay. What's my starting BFS? Put y1 equal to 1, y2 equal to 5, everything else equal to 0. So if you write down the starting basic feasible solution, x1, x2, s1, y1, y2. Okay. So my y1 and y2 are 1 and 5. I write this 2 minus 1, 0, 1, 0, 1, 1, minus 1, 0, 1. I need to calculate my costs, my reduced cost and my costs. What is my cost? My cost for y1 and y2 are 1 and 1. So if I want to calculate my reduced cost vector, it is what? X1, X2, S1 have zero costs, Y1 and Y2 have costs of 1 minus my cost for my basic variables. Basic variables costs are 1 and 1. B inverse A. B inverse A is this matrix, right? 2 minus 1, 0, 1, 0, 1, 1, minus 1, 0, 1. Okay. If you just calculate this, basic variables will have reduced cost of 0. Non-basic variables, the reduced cost will be what? If you calculate this, sorry, it will be 1 times 2, 1 times 1, that is 3. So this should be minus 3. This should be minus 1 plus 1, 0. So this should be 0, I guess. And this should be minus 1. So this should be, I guess, 1. Is that clear what I'm doing? I'm using the cost for y1, y2. And what is the cost of this objective? Y1 is 1, y2 is 5. So total cost is 6. So I have to enter here minus 6. Okay. What's my goal? My goal is to solve this problem to optimality. How will I do it? It's clearly not optimal. X1 is got a negative reduced cost. X1 enters. Theta star is minimum of 1 by 2, 5 by 1. So that should be a 1 by 2, which means my leaving variable should be y1. So gradually I'm moving variables, artificial variables out of my basis. I'm moving them to 0. Do row operations. What are my row operations? In this example, it will be, for example, I can do row 1 by 2. This is row 0, row 1, row 2. Row 0 will be then row 1, row 0 plus 2 row 1, sorry, plus row 0 plus 3 row 1. And row 2 will be Row 2 minus row 1. Okay. So you continue. Okay. You solve this to optimality. Okay. And trust me, you can try this on your own. So continue till you will end with, you keep doing this, you will come to this final tableau. Okay. And this you can check on your own. Okay. Continue. You will get to this. Okay. This is optimal. Okay. Phase 1, optimal. Why? Because all Cj bar are non-negative. Okay. Optimal value is 0. How is this possible? Because y1 and y2 are 0. They are non-basic variables, they're 0. Okay. So you are actually, this means that the original LP is feasible. Therefore, original LP is feasible. Okay. Now we will start phase 2. How do we start phase 2? I wanted my original variables were x1, x2, and s1. So I will now take in this matrix essentially this part is B inverse A, right? The entire thing is B inverse A. But I'm interested only in this part. These are my artificial variables which have gone to 0. So I will just take this part, x1 and x2. The values are 11 by 4 and 9 by 4. That's a basic feasible solution. Okay. I'll just copy B inverse A, 1, 0, 0, 1, minus half, minus half. Okay. My variables are x1, x2, and s1. The only thing I have to do is I have to calculate now reduce cost for this basic feasible solution using the original problem. My original problem costs were -1 and -3. So you have to now calculate new reduced cost for this problem. So C bar, so what are my, so C bar is C1, C2, and X1, X2, and S1. What are my costs for X1, X2, S1? -1, -3, 0, minus the cost for my basic variables. -1, -3. B inverse A. What is B inverse A? It is this matrix. 1, 0, minus half, 0, 1, minus half. So if you calculate this, you will find that this will give you basic variables will have 0 reduced cost, and the non-basic variable S1 will have a cost minus, that's plus half, plus 3 by 2, that's plus 2, minus 2. Okay. And what is the cost of the solution? 11 by 4, 9 by 4. If you just calculate the cost, minus 3 times 11 by 4, minus 3 times 9 by 4. If you calculate it, you'll get 19 by 2, minus 19 by 2. So negative is 19 by 2. So I'm just recalculating row 0 using the original cost function. And now solve this to optimality. It's negative, bring it into the basis and repeat. Continue till you solve phase 1. Phase 2. Okay. Did that make sense or no? Uh, yes. You have to try it out on your own. The key point is I want to, I mean, what is the key point? I want to make the y is equal to 0. It might be possible or not possible. If y cannot be made 0, the LP is not feasible, the original LP. You cannot do anything about it. If y can be made 0, you basically solve an LP to find a basic feasible solution. And then you solve the original LP to find the optimal basic feasible solution. So somehow you're finding the beauty is you're making finding a BFS itself an optimization application of LP simplex. Okay. Okay. We are short of time, so I just want to make one final point before we end. So we're a little bit over time, but let me just make one final point. So, for example, one open question in LPs, okay, which to the best of my knowledge has still not been solved is, so what we have shown so far is simplex method converges in finite time. We never said it converges in polynomial time. Okay. So one open question here is, Are there any pivot rules? Are there any pivot rules for simplex such that it converges always in polynomial time? Okay. This has not been as yet ever shown. It might be true, it might be false. Okay. The answer could be yes or no. For every pivot rule so far, they've been able to create examples where, in the worst case, it can take exponential number of time. You have to go through a lot of basic feasible solution or all of them. Okay. So this is an open question which is still unresolved in LPs till date. Okay. Whether any version of simplex can be ever made in polynomial time. Now there are some people who do research on this which who show that. So one research direction that people have shown is under nice probabilistic models of the data. Okay. So if I tell you something about A, B, and C, and so on, under some nice assumptions on these models probabilistically, there are results which show there are results that show simplex converges in polynomial time on average. Okay, so whatever you mean by average. Okay, so there are results of this nature where you show in the worst case it's exponential time, but on average time it's good. It works in polynomial time. So simplex actually works quite well in practice. Though some of those worst case instances are extremely rare. Okay, okay, we'll stop here. I will see you on Thursday afternoon. Okay, okay. Thank you. Are the recorded classes available elsewhere? It's you can find all the recorded classes on my. If you go to my webpage, I'm all recordings I'm putting up onto a YouTube playlist, so you should be able to find it there. Okay, you can go to my webpage and you should be able to find the link. Okay.